All right, so I'm going to get started. How's everybody doing on this beautiful Friday? Fantastic. So today we're going to go over the homework. I've, I have not graded it yet, but I've gone over it, so I've looked at what people did. Not in horrific detail, but I've kind of glanced over it. A couple of you didn't get it in. I have to say that falling behind on the homework is the kiss of death in every class I've taught. So make sure you stay on top of it. If you miss this homework set, talk to me and make sure you get it done. Also, and I'm just throwing this out as how do people totally bomb in my class? The other way people totally bomb is by not understanding the homeworks when they turn them in, and then not being able to do the stuff on the final. So kind of all of the stuff centers around doing the homework. So it's important that you did it. I'm not actually calling anybody out in specific on that. That's just like a general service announcement of how to do well. I'm going to go over the homework today just so we can talk about what we did and make sure that everybody's on the same page. And also clarify a couple of things in the homeworks that didn't work as well as I wanted them to as homework problems, but that's okay. I will fix them for the next version, but it was more successful than I expected. So we'll go over paper one. I have changed the due dates of the numerical assignments, so the next numerical assignment is now due Friday and not the following Friday. The reason for that is the schedule had a paper homework due this Friday, which has not gone up yet, and I'm not going to give you less than a week to do a homework because that seems unsporting. So the numerical homeworks are relatively painless. There'll be office hours on Thursday again, and then there'll be another homework due next Friday. So after I do the homework, then I'll do Kepler 1. I'll prove Kepler's first law, which is the longer of the derivations, so I did it last. And then I'll talk about the virial theorem, and I'll show you my better proof of it, which makes more intuitive sense, if you're me, anyway. Okay, let us talk about the homework. Everybody did pretty good. I'm just going to run through them kind of fast. Feel free to holler or ask questions if there's something that I say that if you didn't do it that way and you want to talk about that, or so here's the space where you can talk about the results. So first, describe RA and DEC. No, I just said right ascension. So right ascension is the distance on the sphere, on the celestial sphere, in angles around the celestial pole from the vernal equinox to the star. There's a lot of things that need to go into it, so I don't have a specific rubric that I'm going to work off of when I actually grade it, but at the moment. But those are the things that we need. So we need to see when you're talking about how is RA defined. It's defined on the celestial sphere around the equator of the pole of the Earth, not the one that's transverse to the pole of the Earth, around the pole of the Earth, relative to the vernal equinox, which is actually a point in outer space, even though it's when is it? What's today? It's the 15th. So the vernal equinox is next Wednesday. Is that right? Is that the 21st? So the vernal equinox is coming up, so you can go see the thing that we're talking about by staring up in the sky. Okay, so what are the RA and DEC for Alnitak, Alnaham, and Minitak? So these are three stars that you can look up. Hopefully I think everybody did okay looking these stars up. And that's all I wanted you to do. Some of you had said that, oh, hey, I just looked it up because I don't know how to compute it. That is the thing to do. Because there's no way to compute these. These are measured quantities. So you should get 5 hours and 40 minutes and 45 seconds for Alnitak. And minus 1 degree and 56 minutes from its declination. You get 5 hours and 36 minutes for Alnaham and 5 hours and 32 minutes for Minitak. So now the way RA and DEC works, is it's in hours around the sphere. So as the Earth turns, so does whatever is above us. So if Mintaka rises at 10:07, when does the next star down rays come up? You can see that it's about 8 minutes later, because this is about 8 minutes after that. And RA, while it's also a coordinate system, is also a useful coordinate system. Yeah.
How am I supposed to know which one rises first, just because it's a lower time?
Yes. Time goes that way. So the reason that the way that you can tell from that is that's how I asked the question. So I said that's what's going to come up second. So, but yeah, if it goes from that direction and increases that way, and the Earth spins in that direction, so the number kind of goes down as you are pointing at one spot. Does that make sense? Let's see. Given an ellipse with a semi-major axis A and a semi-minor axis B and an eccentricity E, show the following things. So the first one is that B equals A squared plus times 1 minus E squared, which I almost did in class, and then I decided to not and made you do it. And then the other one, which I didn't do in class, is prove that R equals A times 1 minus E squared over 1 plus E cosine theta, which is kind of an awful expression, but it shows up so often that it's useful to see where it comes from, and it's useful to really put your hands on it. So I'm going to go through these real quick. You are a little crooked. Oh, and I also apologize for not having gotten the videos of the lectures up on time. All the videos are up now. So, which really matters the most right before the homework, which is when I didn't have them up. Sorry. Hopefully they'll go up more soon. Okay. We have an ellipse. My art skills are bad, so take all of my art with a grain of salt. So we have a focus here and a focus here, and the center here. And by definition, this is AE. This is A. This is the center. This, from the distance from this focus is R prime. The distance from this focus is R. And B is here. So from the definition of an ellipse, R prime plus R equals 2A. That's how an ellipse works. It's like, this is all you need. Just start from here, and you can derive all of the rest of this stuff. You gotta draw the right picture first. So if I'm gonna pick this point, so this is true for every point on the ellipse. Not this ellipse, but an actual ellipse. This is, I failed art in kindergarten. That's why I got into math. So how do I sort this out? So this is true for every point around the ellipse. So if I pick this point that's halfway between the two foci, then R and R prime are the same. So I can say R prime equals R. So then 2R here equals 2A here. So R equals A, which is nice. So the semi-major axis is the distance to the semi-minor axis from the focus. Does that make sense? You just see that. So then how do we find out what B is? Well, I just write down Pythagorean theorem. So B squared plus AE squared equals R squared, but I know that this equals A squared, and I move this to the other side, factor out an A squared, and I'm left with B squared equals A squared 1 minus B squared. Everybody happy with that? Does that make sense? I'll be able to see what I'm doing. Okay, so that one's relatively painless. I think everybody got it. This next one is a little bit trickier. I might even draw a better ellipse for this. Actually, I'm not going to draw the ellipse part because I'm going to mess it up. So let's just start with the focus. So what are we trying to show? That R equals A times 1 minus E squared over 1 plus E cosine theta. So if I take a point here, so I got my ellipse. is like this. I'm going to take a point here, and this works regardless of where I am. So the math that I write down doesn't care about the point that I actually draw. So I'm going to take this point on the ellipse. I got this. This is r prime. This is r. This is the center. So this distance is AE. So this distance is 2AE. Now we're going to relate everything to this angle. That's really the stunt. The stunt for so many problems in physics is drawing the right picture in the first place. So we're going to do everything from this angle. Why this angle? Because this is the angle measured from perihelion, which is kind of comes naturally out of the Kepler's first law proof, but also makes the most sense. So this angle is the angle that we're using. So we want, is there another color of chalk here? What do you think the odds are that there is? There's white. There's all this pink dust. There must be pink chalk. Or murder with chalk. That's grisly. Okay, so this and this, we got a triangle here. So this distance is what? This is r cosine theta. R cosine theta. And I want to get rid of r prime. So what do I know about r prime? I know that r prime plus r equals 2a. Okay, that's almost useful. And then the other thing I know is this big old triangle. So this triangle says 2ae plus r cosine theta. 2ae plus r cos theta squared plus this vertical one, which is what? It's going to be r sine theta plus r sine theta squared is r prime squared. Okay, so from this I'm going to just rearrange, and I've got r prime equals 2a minus r. So I take this and I plug it in here, and I'm left with 2a minus r squared equals 2ae plus r cosine theta squared plus r sine theta squared. Wait, here's the point where I often jump ship because the rest of this is just algebra. And that's boring to watch me do. It's more fun to do it yourself. That's not true. It's never fun, but it's more useful to do it yourself, which is why I had you do it. So anyway, we can do it real quick. So this is going to be 4a squared minus 4ar plus r squared equals 4a squared e squared plus 4ae r cosine theta plus r squared cosine theta squared plus r squared sine theta squared. This is a cosine theta. My hand got a little. Wait, so let's see. What's the one thing that I know about cosine and sine theta? Cosine squared plus sine squared is 1, right? I've got an r cosine squared and r sine squared. This just becomes r squared. Sweet. And then I've got another r squared over here. Oh, hey, those cancel out. It's positive on both sides. So then this is the r that I'm looking for, and we can get rid of, let's see. So this r cancels. I think all my 4's cancel. And let's see, what else do I have? So I've got 4a squared minus 4a squared e squared. Okay, so that's going to be my top part. And then I've got divided by what's left is a e cosine theta. Oh, I missed this term. Which gives me 1. Okay, now here I'm at the bottom of the algebra, and I probably screwed something up, but I get the right answer of r equals a times 1 minus e squared over 1 plus e cosine theta. So aside from me not caring about the algebra enough to do it properly, does anybody have any questions about how this all works? So this bit here, you just solve R, and it's straightforward. You get this. The setup is the interesting part, and that's kind of the tricky part where people get hung up, is setting the things up so that you've got an equation that you can extract. Does anybody have any questions about that one? Pretty happy? Right. Next. Geosynchronous orbits. So, by matching gravitational force and centripetal acceleration, find an expression for the circular velocity of a satellite orbiting a mass m at a radius r. Assume it's round. So, I ask you to do this for several reasons. So this is a very important thing to get your head around. One of the reasons is it's a very nice proof of Kepler's second law. And one of the reasons is it's a very nice proof of the virial theorem. It's really great. It's a really great little nugget of math. I have not shown you the virial theorem yet. You guys read the virial theorem, right? That's good. Okay, so I've got a planet. And I've got a satellite going around the planet at some velocity. So it's got some velocity v, and it has some acceleration. So it's just moving on a perfectly circular orbit. It will stay on that circular orbit forever. What is its acceleration? V squared over r. Okay. So if that's not obvious to anybody, let me know. So I'm orbiting at a radius r, and I've got some velocity v. My acceleration is v squared over r. And you can see this by taking the derivative of the position vector. There are several ways you can see it, but it's a useful thing to just remember. The centripetal acceleration is v squared over r, and the force of gravity per unit mass, so this is an acceleration, so force per unit mass is my acceleration, right? So gravity is providing the centripetal acceleration, is equal to g times the mass of the planet over r squared. So I set these two equal, and I get v squared equals g m over r. Now, this is very useful because of several things. First, it tells me virial theorem. How do I see that this is virial theorem? What is virial theorem? Virial theorem says that 2ke equals the absolute value of the potential. And I'll talk a little bit later today about why I care about this and what it does for us. But you can see that this says the same thing, right? I have a m and a 1/2 that I multiply by 2, so my 1/2 goes away, and my m cancels. Okay, so this is twice the kinetic energy is v squared. And this is just potential energy. So all this says is 2k equals p, right? So that's a very useful thing. So this is virial theorem. It's also a proof of Kepler's third law. So how do I know that? So I know that velocity is what's the distance that I go around this? It's going to be 2 pi r, right? So v is 2 pi r over the period. So the period, let me call it p for period. It's always been t, but I don't know. So then p equals 2 pi r over v equals 2 pi r times the square root of r over the square root of gm equals 2 pi r to the 3/2 over the square root of gm. Everybody follow me here? Pretty happy? Okay, so then if I square both sides, I'm left with, hey, p squared equals 4 pi squared over gm times r cubed. Hey, that's just Kepler's first law, third law, right? P squared is a cubed. So this is the same thing. In Kepler's third law, we're talking about the distance from the sun to the planets. This is the same physics, same thing. Okay, so next, I said, solve for the radius such that the period is 24 hours. So that's easy, we just solve this again. So we get r equals P squared GM over 4 pi squared times, oh, that's it, to the 1/3. And then you plug in some numbers, which I'm super not going to do, because I really don't like numbers. Numbers are really boring. I like shapes and relationships. So you plug in numbers and you get, I think it's 42,000 kilometers. Is that right? I wrote it down. Yeah, 42,000 kilometers. Cool. So then I asked, what's the difference between geostationary and geosynchronous? Because that's what we just worked out. This is now orbiting the planet at the same rate that the planet's going around. So now you can set your satellite up in 2 ways. So if my satellite looks like, so here's my planet, here's the axis of my planet. If my orbit is in the equator, is along the equator of the Earth, then I can park over one spot on the Earth. That's the only place I can do it. I can't park over a spot right here because it's up there. I can only park over things that are on the equator. If I try to get on this spot, then I need to be in a polar orbit. And I can be in a geosynchronous orbit by passing over the same spot every 24 hours. So the Earth turns around, my orbit goes around. So I view the same spot every day. Versus a geostationary orbit where I view the same spot all the time. Does that make sense? So these are all useful for weather satellites and things like that. So it's a very useful place, the geosynchronous orbit. Okay, the satellite SPECT-R. Oh, and I realized that I wrote this problem in a way that's a little confusing. But I'm going to leave it that way because I actually like the way it's written. So the satellite SPECT-R was a Russian satellite in orbit at 10 Earth radii. Assuming an angular resolution of 1 microarc second, what's the farthest object that this can measure? So 10 Earth radii, I think, might have thrown a couple of people off because that's not the baseline. That's the size of the telescope. I'll explain this when I get to telescopes, but when I have a telescope, you know what I should do is just draw a circle in Sharpies, but I always have a big circle. Here's my telescope. Now it's a telescope. What sets the angular resolution of this telescope is not the niceness of the glass, and it's not how much glass there is. It's just the angular diameter of the telescope. Yeah.
So this meant over the period of its orbit around the Earth, not the 6 months as in like previous.
Yeah, its angular resolution isn't as good as over 6 months. So I will grade accordingly. I recognize that it was a confusing question, so I'm not going to knock anybody off if you did it that way. I should have written the question better. There's a couple of those throughout, so I appreciate your patience as my copy editor drinks on the job. So the 10 Earth radii isn't the most. So the way to answer the question is just to say distance equals 1 over the parallax in arc seconds. And this is the distance in parsecs. That's all you have to do. It's very simple. Because the rest of the geometry was taken care of by the fact that an arc second per AU is a microarc second in radians. So what is this? If I said that the angular resolution is a microarc second, we divide a microarc second by an arc second, and we get a micro. We get 1 over micro, which is 10 to the 6. So we get 10 to the 6 parsecs. Make sense? So this question is going to show up again when I say, now compute the diameter, compute the angular resolution of this telescope. So the way this telescope works, it was a very cool thing. If I take, so the angular diameter determines the resolution. So if I take a telescope like Keck, which is a huge piece of glass, and I put black paper over the inside 80% of it, I don't decrease the angular resolution, I just decrease the light collecting power. Does that make sense? So if I take 2 radio telescopes, this works in the radio, but not in higher frequencies. I take 2 radio scopes, okay, now this is the Earth. Right, so now this is the Earth, and I'm going to put a radio telescope here in Puerto Rico, and we'll all mourn the loss of our favorite radio telescope in Puerto Rico. There's a radio telescope. The biggest telescope in the world was Arecibo in Puerto Rico, which you might have seen what was it, Goldeneye, I think it was in. Anyway, it's a gorgeous telescope. And it was part of a lot of very long baseline interferometers. That telescope collapsed, unfortunately. It was one of the most depressing things I've ever seen. So there's a radio telescope here. There's a radio telescope here, and one over here, and one down here. I don't need to I can make one telescope out of all of these telescopes by just writing down the photon to disk. So the photon comes in, photon goes up and down, writes a wave. I write that photon down to disk. Well, I convert it to voltages, and I write the voltages down, but it's the same thing. So then I have a record of all the photons that came in, and then I can then I write that down to disk, and I have a very accurate clock, and I just pretend that I had one telescope. And then we have a telescope that's got bonkers angular resolution. I'll talk more about this later. So okay, a megaparsec. How am I for time? Going slow. Given Kepler's third law, if you were to fit a line to this, what would you expect M and C to be? Yeah, this is what they saw that black hole with.
Are we trying to launch that right into space like in the next 10 years?
That's what this SPECTAR telescope was. Sorry, I totally zoned out on the last bit. The SPECTAR telescope was this, but with one telescope way over here. What's that? It's possible. It's possible that there's another one because it's a very cool idea. Because you can make radio telescopes really big in outer space. You just need to unfold them. We know how to unfold stuff. Although everybody worked on James Webb, which did this massive, beautiful unfolding of its mirror. Everybody who works on that said they would never do it again. So, radio telescopes are a lot easier to deal with than optical telescopes because radio waves are this big. Yeah, we did.
Always more.
There's always more, and with something like James Webb, there's always more. Okay, so let's fit Kepler's third law into a line. So we have p squared equals a cubed. Now there's a k here. That's for units. That's if I want my period in fortnights and my distance in femtoparsecs. Then I've got to have some k. But if I use my period in years and my distance in AU, then I don't have to have a k there. So let's leave the k there just for fun. So I want to turn this into a line. Was that 14 days? 14. Yeah. Or it's a great way to spend a lot of money on loot boxes, I guess. What is that?
Two scored Fortnite.
I forget what that's from.
Lincoln.
Oh, thanks.
Yeah.
I know it's space. I've never would have.
On the back of the page. I don't know why I know that.
It's all right, man. Something to stick with you.
I did.
So okay, what am I going to do? I want the log of P and the log of A. So I'll take the log of both sides. And so the left-hand side, the 2 comes down, and I'm left with 2 log of P equals 3 log of A plus log of K.
Why do you do natural law?
I like natural logs. Natural log is the jam. It doesn't actually matter which log I use. So I can use log 10. I think I use log 10. I realize now that you asked that question. Doesn't matter which log I use. We'll just make them 10. Now we're good. Logs are magical like that. Logs is my favorite function. Is that?
I like the natural log.
It's great. It makes huge numbers little, right? Although the log, anyway, a log just jacked up my supercomputing scan, which I can explain, but it would take way too long. I would not get through everything I want. So okay, I rewrite this. I just take a log of this and I rewrite it like that. That's not what I have up there. I got to get this 2 over here. 3 over 2 log k. There's a 2. We'll just absorb it into k. Right. So if I'm going to write this as log p equals m log a plus c, then m is 3 halves. That's the important part. That's what I'm going after. And then c, this is just units, is going to be log k, whatever your units are. So some of you had a k in there. That's cool. That's the good one. Does that make sense? So we're turning this thing, which is powers of stuff, into lines. That's a thing that we really like doing as physicists, is turning everything into a line whenever we can. I'm probably going to make you guys do some linearization of complicated systems because that's what we do as physicists. We make everything else. Yeah.
If we had specified P's in years, A is in astronomical units,
Uh-huh.
and then just had it as M is 3/2 and C is nothing.
Yeah, that's accurate. Yeah, so that's exactly right. So if I didn't do it did it in the other units and K is 0, then C is 0. So log K is 1. No, K is 1. Log K is 0. Oh. And then I asked you to plot some stuff, which I haven't done, but I know that people have been proving Kepler's third law with these planets for like 400 years. Maybe 200 years. I can't remember when did Galileo make the telescope. Long time. So hopefully everybody made a plot. I saw that there were some plots made. We might make more plots later. But the slope of the line that you get out of it is 3/2 when you plot this. What's that? How did I get the points?
Yeah, so I don't know why I just scrolled, because I got that part.
Yeah.
That's
So the
why
points.
I
Oh, so
plotted.
what a plot? You mean what a plot out of this?
Yes.
Yeah. So the distance is the distance from the center of Saturn to the planet. So that's its planetary radius. So that'll be A. And then the period is the orbital period in days. And it doesn't really. So since this is a different system, you can leave it in days, and it works out just fine. You just have a different concept. Totally gonna kill myself there. So does that answer your question? Okay. Does anybody else have any questions about number 5? Number 6 also is one piece of information that I realized that I was missing in the problem. So hopefully you sorted it out. Yeah. Oh yes, I'm sorry. You shouldn't use the diameter. You should do what he did and read the chart first, not what I did, which is just look at the number that says km. This is the radius. This is the orbital radius.
It's just that longitude.
No, that's it. Well, so when you do the plot, then you take a log of each one of these and the log of each one of these, and you plot that.
So,
Oh, oh,
That's all. We'll sort it out. Like I'm a real easy grader. So as long as you put in some grind and got close, well, you'll be all right. Okay, Pluto has a mass of blah, 1.3 times 10 to the 22, and its biggest moon, Charon, has a mass of 10 to the 21. So compute the reduced mass. I wrote that down. The reduced mass is just M1 over M2 over M1 plus M2, and you should get something that's about halfway between the two is 1.3 times 10 to the 21. No, is that right? Yeah.
That's what I got.
Oh yeah, it's pretty close to the smaller one, right? That's how it works. I'll show you. So I've got M1, M2 over M1 plus M2. Now in the limit of M2 is very, very small, what do I get? Is that? Yeah, you get the smaller one. So if M2, let's say that M1 is much, much bigger than M2. That means I can cancel out M2 from the denominator. And then this cancels out this, and I'm just left with M2. So when you have a huge imbalance, the reduced mass is the smaller one. And the total mass is the bigger one. Which is kind of magical about this system, because like the aesthetics of, like, I take two objects and I don't care what they are, and I turn them into one object orbiting another one. And that math all just works perfectly if you've got a sun and an Earth, because the reduced mass and solar mass and the total mass just look like the Earth mass and the sun's mass, but it's all consistent. So anyway, I'll talk more about that in a minute. Okay. So compute the location of the center of mass of the system. So several ways to do that. And this I realize is not I should have worded this problem differently too. So the easiest thing to do, what I needed to do is tell you what the distance between Pluto and Charon are. So if you have the distance between Pluto and Charon, we'll call this R, then I know that the center mass is here, and R1 is M2 over the reduced mass times R, and R2 is M1 over the reduced mass times R. They're different by a minus sign. Does that make sense? Pretty good? So I can sort out easily, since I have the masses of both the planets and the reduced mass, if I had properly given you the distance in the first place, which is what was missing from the problem, then you can compute R1, which is here. So the center of mass is going to be the mass of Charon over the reduced mass times the distance is going to be the distance of the center of mass above the center of Pluto. And you'll see, if you work out the numbers, that distance is about 18 times the radius of Pluto. So these two things are orbiting at an empty space. Let's see, derive an expression for the escape velocity of a planet with mass m and radius r. So the escape velocity, you find the escape velocity by just asking how much energy do I need to unbind myself from the planet. This is another, yeah.
Before you move on,
Yeah.
you use the mass of Charon, right? Then why is it the distance from Pluto?
I thought yesterday you said it was
That's a great question.
If we didn't use, if we used mass of Pluto, wouldn't we get the distance from Pluto?
I'll show, hang on a second, let me explain. So this is R1 and this is R2, right? So let's say that R1 is a lot bigger. So the center of mass is going to be closer to that one. Does that make sense? So if I have this as the distance, then R1 is M2 over mu times R. It's the smaller one. So the distance here gets the smaller distance. And R2 equals minus M1 over mu times R. Why is it backwards? Why does R1 go with R2? Because the center of mass is closer to the bigger one. So it's got to have a smaller mass in it.
Because it wasn't what it said in the textbook.
Was that?
It said R1 equals M1 over it.
Oh, it's the other way around.
I would.
I'm not second guessing myself. I'm just pulling it up as a demonstration.
It says that R1 is equal to negative mu over M1R.
What's that?
R1 is equal to negative mu over M1. R.
Well, I've made mistakes before.
Because 18 times the radius seems a bit much.
18 times? No, that's about right though.
It's much from it's only 0.1 R.
Oh, it's not than where I was. Sorry, not mu m. Sorry. These are the R1s, and this is R1 and R2. So this R1 is M2 over M1 plus M2R. So it's M1 over the total. And that's what you need to use. because it's the relative distance of the center. Does that help?
Yeah,
Um,
I guess I was looking at
Yeah, it's possible. Let's see.
involved
Let's see. Is there another one?
yeah, those are.
This one is easier to think about. This one is the one the way I was explaining it. So the center of mass is going to be closer to the bigger one, right? So intuitively we know that I've got two distances. The one that's above the center of mass has got to be smaller. So so R1's got to go with the smaller mass. The other way to write it is R1 equals mu over M1, which gives you the same thing if you just rearrange the math a little bit. But again, R1 has got to be the smaller one, and here we're dividing by the bigger mass, which gives it the smaller number.
Who is that? It's closer to here.
Closer to
Closer to
the
the
other one. Yeah.
Okay.
Does that make sense? Almost. Okay. Bonk.
Does it matter which one you say is negative?
No. But it does matter if you use mu or m in the denominator. And if you're using mu like I started to, you'll get the wrong answer. But if you use the total mass, if you use mu, then you have to do it upside down. So as long as you were consistent and did the right thing. Where am I? I can't see you. Oh man. All I'm gonna do is get through the homework. Okay. Okay, derive an expression for the escape velocity of a planet with mass m and radius r. So here's my planet, here's my sun center, here's the radius. The potential energy is gm m over r, and the kinetic energy is 1/2 mv squared. So I set these two equal, and I'm left with 1/2 v squared equals gm over r, or v equals 2gm over r square root of this. Now what's the difference between this and virial theorem that I wrote down before? The virial theorem doesn't have this 1/2. Now normally I don't care about a factor of 2. So virial theorem doesn't have a half here because they come from very different places. This is energy, and virial theorem is about forces. So I'll explain when I get to it, and I'll get to it Monday. So V is 2gm over r. So now the escape velocity, if I use the mass of the Earth and the radius of the Earth, I should get an escape velocity of 11 kilometers a second. So then the other thing I asked you to do was the sun, the escape velocity from the sun at the radius of the sun. And what did you guys get? Ballpark.
600.
You got like 600 kilometers. And then the third thing that I asked you to do, and I worded it wrong. This is a glitchy homework set, I apologize. Try to make the next one better. I worded it wrong, but you guys did some useful stuff, and some of you did what I wanted, and some of you did what I said. Both are fine answers. I said to compute the escape velocity from the sun at the radius of the Earth, but I meant the orbit of the Earth at 1 AU. Some of you did the mass of the Earth at the radius of the sun, or the radius of the Earth, which is a super, super deep potential load. You got like 6,000 kilometers a second as the escape velocity. Totally valid. That is what I asked for. But what I was looking for was the escape velocity from the sun at the solar radius. So this is how do I unbind from the sun? And that's what leaving the solar system is. And you get a value of about 42 kilometers a second from that. So it takes 42 kilometers a second to leave the solar system. To leave the sun from the sun, it takes 600 kilometers a second. That's a substantial velocity. What about to get to the sun? Realistically, what you need to do is say I've got the energy of leaving here versus the energy of getting from here to here. So that's going to be the square. If I square them and take the difference, the energy from getting from here to here is going to be 600 squared minus 42 squared. Whatever that is way bigger than 42, right? So getting from here to here is the energy that it needs to hit the sun, which is something like 600 squared, 40, it's like something like 500. It's a lot, right? Versus getting out of the solar system is a lot easier. It's because you got to get down that potential well. It's a crazy deep potential well. Yeah.
So D is asking, like, you're on Earth and you're trying to escape the sun?
Yeah.
Okay, I totally did not.
That's, I didn't word it right. That's an error on my
A lot
part.
of people accidentally calculate escape velocities of like a black hole.
It's a mix. Some people did what I said, and some people did what I wanted. Yeah.
I think the only reason I realized it wasn't like literally just the radius of the Earth is
Because of E.
like I did it wrong the first time, and then I read E and I realized, oh, it was supposed to be.
I appreciate that. You can pick up what I was asking from
I
context.
did something else entirely. I like integrated from this like from the sun radius to the Earth's orbital radius, and I don't know. I got a number that was smaller, but not 42 kilometers.
Okay.
I don't know what I did.
That's cool. I'll look at what you did and carefully and leave you some feedback.
What if I have crazy big numbers in meters per second?
Well, 32 kilometers, 600 kilometers a second. I don't. Could you take a second and think about how fast 600 kilometers a second is? You'll get something in the millions, right? It should be in the millions. Shouldn't be in the billions.
Error.
Did you get something like 10 to the 300?
10 to the 12, so.
That's many. What are your units in meters? That's probably too many.
I don't know what I
That's all right. There's a lot of easy. There's a lot of square roots and stuff where you can make weird numbers this way.
Okay.
Ah
That's
man,
fine.
2 minutes left. Okay. Let's see. I got 2 minutes left, and there's 3 problems. What do you? What's that?
Nice.
Which one would you like? Thanks. Which 9?
Yeah.
Is 9 cool?
Yeah.
Okay. Second. Jesus Christ. All right. I've gotten so used to having homework sets that I've used a couple times and actually proofread carefully. I'm embarrassed by these little things, but they're a natural part of doing something for the first time. So you learn by screwing stuff up. That's what I firmly believe. Okay. Kepler's second. Is that right? Yeah, we just proved Kepler's third in a really nice way, and really my favorite way to do it. Just because I like the real so much. Okay, so Kepler's second is equal area. For equal time. And so what we need to do is first set up an expression for the area. And we'll have an ellipse. Terrible ellipse. Focus is here. Right? So we need an expression for the area here. And there's a couple ways you could think about it. The book just starts off with just the area integral element. So in 2 dimensions, in polar coordinates, the area element, dA, equals r dr d theta. That's thing 1 that I want to make sure that everybody's comfortable with. If everybody's comfortable with that, then I'll move on. Not holler, and I'll spend a minute with that. The basic idea is when I've got polar coordinates, I've got my radii go out like this. This is d theta. I drew it as a macroscopic angle, but really d theta is tiny, right? D just means a tiny thing. And dr is going to be the same as we go out. D theta is going to be the same as we go out, but the actual area of this thing gets bigger as you go out with r, by r d r d theta. So the side length here is r d theta, and the side length here is dr, so the area is r dr d theta. That doesn't sound obnoxious that I'm carefully explaining that, but I feel like that's one of the kind of core pieces of calculus that's hard to get your head around. Is what's the area element? What's the volume element in 3 dimensions? In 2 dimensions? So we want to get rid of r, so we'll just integrate an r. And what's the integral of r dr? 1/2 r squared. So the a then becomes 1/2 r squared d theta. And I'm going to rewrite this as 1/2 r d theta. And r d theta is v theta. So if I've got some r and I've got some d theta, oh, no, it's not a v yet. Why is it not a v? Because I haven't gotten a time yet. Let's get a time, yeah.
Why'd you start with d squared again?
Well, the book just calls it dA. He says dA is r d r d theta,
Okay.
but there's two d's here,
Oh,
so I need to have two d's here.
Okay.
Is it because it's a double integral?
Well, it's because it's a differential, but this differential has two little differentials in it. This isn't a super big point. The book left it off. People leave it off all the time. I put it here because this is two small things, and I'm going to get rid of them and be left with one small thing.
Yeah, because when I was going through it in the book, and they just used the I was like, how? Because they would just have area, but you saw the data, and I was kind of confused. So the fact that the square is going to makes more sense.
Yeah, and he starts with dA equals r dr d theta, and then he gets dA equals 1/2 r d theta.
Yeah.
Which, you maybe even didn't notice that, but when I was going through it, I was like, yeah, that doesn't make sense. So, the area, now another way you can think about this as 1/2 base times height. Area of a triangle is 1/2 base times height. The base is r d theta. The height is r, so 1/2 r squared d theta. Make sense? Is my area. Now I need to turn this into a time derivative, so I'll divide by dt, and this is physicist math and not math math. Physicist math lets me do that. So dA dt equals 1/2 r squared. Let's put that on the d theta dt. The d's always have to go together because you can't have a d by itself. So dA dt, now this is the thing that we're talking about, and what Kepler's law says is that this is the thing that's constant. But on the right-hand side, I've got r, which is changing in time, and d theta dt, which is changing in time. So the fact that these actually aren't changing in time, they're changing in time in the opposite direction is a very cool thing. So let's think about what this is. I've got 1/2 r, and then r d theta dt. So this is d theta dt here, and if it's moving in this direction, that's an angular rate in radians per second. I want to turn that into a linear rate in kilometers per second by multiplying by r. This is v theta. This is the theta directed velocity. So dA dt is just equal to 1/2 r times v theta. Okay, is everybody okay so far? Or at least follow the parameters. Was that
1/2 r or 1/2 r squared?
1/2 r v theta? So I've got two r's here. One of them goes with the d theta dt, and one of them is hanging out. So I've got r v theta, right?
So r d theta to t is equal to v theta.
That's right.
R's are position.
Yeah, r's where I.
The radius. Okay.
Yeah,
R's
r's
the radius. So it's radius times the change in theta,
Yeah.
which is okay.
Which is
okay.
equal to this length.
Okay.
is equal to
I say that.
Good.
Yep.
d theta dt.
Okay, so then the next bit. So r v theta. I haven't shown that this is constant yet. So the next bit, and now I'm over time by 5 minutes. None of you guys have class after this. That's kind of nice. I can tell because.
No one's run out.
Nobody's running it. So okay. 1/2 r v theta. This, once you've been doing these things long enough, you recognize that this is just the angular momentum. R v theta is the angular momentum. This is 1/2 L, angular momentum per unit mass. Because angular momentum is mass times r cross v, which is just r v theta. When you do the cross product, all you get out of the cross product is v theta. That's the only thing that survives. Everything else dies. So, dA dt is 1/2 L over mu. And L is constant. from some weird vector identities that you did in the previous one. So L is constant, so d a dt is constant. Also, what this means is that r and v theta vary opposite each other. So where you are and where you're going are oppositely related. Okay. Schedules are for dorks. Because I still want to go over the virial theorem the way I want to. So do the reading that I assigned on Monday, and I'm just going to do virial theorem super fast and then make you guys do it for a homework. So I really like the virial theorem. It connects so many things. It's such bullshit. It's really never right. But it works all the time for being wrong. It's beautiful.
I was so confused for a second because we were writing b theta. The theta was big enough to where I thought it was b times theta. And I was like, what kind of fucking math is that?